Hello everyone, welcome to Organic Chemistry. Today we will begin our study of organic compounds by learning the simplest type of organic compounds. In this chapter, we will apply the principle of bonding, shape, and reactivity to our first family of organic compounds, which is alkanes and cycloalkanes. Because in this family, we do not have any functional group. Therefore, both alkanes and cycloalkanes uh, are much less reactive than other organic compounds. And for this reason, most of this chapter will focus on learning how to name these compounds, how to draw their structures, as well as to understand what happens when rotation occurs about their carbon-carbon single bonds. Alkanes are a member of a large group of organic compounds known as hydrocarbons. A hydrocarbon is a compound which is composed primarily of carbon and hydrogen. There are four classes of hydrocarbons which we will learn later, and alkanes are one of that class. Alkanes are also known as saturated hydrocarbons because they contain only carbon-carbon single bonds. Saturated means that they have carbon atoms which are bonded to maximum number of hydrogens. So those hydrocarbon compounds in which carbons are bonded to maximum number of hydrogens are known as saturated hydrocarbons. Therefore, alkanes are saturated hydrocarbons. On the other hand, unsaturated hydrocarbons are those hydrocarbons in which we have at least one or more carbon-carbon double or triple bond. In case of unsaturated hydrocarbons, we have a lesser number of hydrogens as compared to saturated hydrocarbons. So therefore, we can now define alkane as a saturated hydrocarbon whose carbons are arranged in an open chain. On the other hand, cycloalkanes are those saturated hydrocarbons whose carbons are arranged in a cyclic form. Alkanes are also known as aliphatic hydrocarbon because higher members of alkanes resemble those molecules which are found in animal fats and plant oils. And the Greek name for fat or oil is alifer. Therefore, from that name, the hydrocarbons, saturated hydrocarbons, are also known as aliphatic hydrocarbon. So the Greek name for fats and oil is alifer, Eleipphar. This table classifies all four classes of hydrocarbons. As I mentioned earlier, alkanes are one of those four classes. Mainly, hydrocarbons can be divided into two categories. One is saturated, the other one is unsaturated. Under saturated hydrocarbons, we have alkanes, which will be studied in this chapter. And briefly speaking, alkanes are those hydrocarbons where carbon atoms are bonded to maximum number of hydrogens and they only contain carbon-carbon single bonds. Unsaturated hydrocarbons are subdivided into three categories. First category is when the carbon-carbon chain has a double bond. So this category of compound are known as alkenes, and we will study alkenes in chapter 5 and 6. And second category is those unsaturated hydrocarbons where we have carbon-carbon triple bond. These kind of compounds are known as alkynes, and we will study these compounds in chapter number 7. And the fourth category of unsaturated hydrocarbons are arenes. Arenes are those compounds which contain aromatic rings such as benzene, and this category of compounds will be studied in next semester in Organic Chemistry Part 2. The smallest and simplest hydrocarbon is methane. In methane, we have one carbon bonded to 4 hydrogens. In methane, carbon atom is sp3 hybridized, and in chapter number 1 we learned that if a carbon atom has a sp3 hybridization, it will adopt tetrahedral geometry. So in other words, in case of methane, carbon will have a tetrahedral geometry and all 4 sides of a tetrahedron will be connected to carbon. A ball and stick model of methane is shown here. In this model, the black sphere represents carbon and blue sphere represents hydrogen. In tetrahedral arrangement, we already know that each bond angle is 109.5 degrees. Another example of an alkane is represented here. This is the ball and stick model of an alkane with 5 carbon atoms. The name of this alkane is pentane. We will talk more about the naming a few slides later. And as you can see that each and every carbon in a long chain hydrocarbon such as alkane still has a tetrahedral geometry. Therefore, each and every angle is 109.5 degrees. There are multiple ways to draw the structure of alkanes. For example, structure of 3 different alkanes are shown here. First one has a 3 carbon long chain, and the second alkane has a 4 carbon long chain, and the third one has 5 carbon long chain. This kind of structure is known as ball and stick model. In ball and stick model, each atom is represented by a different color sphere or a ball. For example, black sphere represents carbon, and in this picture the blue sphere represents hydrogen, and each bond is represented by a stick. So therefore this model is known as ball and stick model. Ball and stick model is extremely useful to understand the 3-dimensional shape and bond angle of alkanes. However, it is not very practical when we use alkanes to write the chemical reaction and other properties where the structure of alkane has to be shown. So for more common structure is line angle formula. In line angle formula, we represent alkanes with lines. In this formula, hydrogens are not represented. A line represents a bond between carbon-carbon, and it is assumed that at every end and at every bend there is a carbon atom. Now we understand that carbon is sp3 hybridized and it has 4 bonds. Therefore, number of hydrogens connected to each carbon is already understood. For example, this carbon atom at the end is already bonded to another carbon which is at the middle, so it already has 1 bond, and we understand in tetrahedral geometry carbon needs 4 bonds, so remaining 3 bonds are bonded to hydrogen which are not represented. So it is understood that there are 3 more hydrogens connected here. And similarly, in the middle one, it's already bonded to 2, so it's understood that 2 more hydrogens are there, but those are not represented. So this kind of structure is known as line angle formula. So for 3 carbon long chain, so this will be the line angle formula. For 4 carbon angle chain, so we show the structure by a zigzag lines. So remember, each corner and end represents 1 carbon. So the last one has 1, 2, 3, 4, and 5 carbon chain, which is same as this one. And finally, we can also represent the structure of alkanes by using structural formula. So in this case, we do not show any bonds. We can So this would be the structural formula. In structural formula, we show all carbons and hydrogens and number of those atoms. Structural formula does not represent the actual shape or bond angles. It only represents how many carbon and hydrogens are present in the alkane. By definition, constitutional isomers are those compounds which have same molecular formula but different structural formula. The meaning of having different structural formula is that the two compounds either have different kind of bondings or they may have different kind of connectivity. For example, with this molecular formula C4H10, there are two possibilities of structures. In first possibility, we may have all 4 carbons in a linear straight chain, and then hydrogens are connected to complete the octet of the molecule. Now the second possibility is that we may have 3 carbon as a linear chain and the fourth one may be connected to the middle carbon. Now as we can see that the connectivity is different, although the kind of bonds are exactly the same. So in this case, again we will connect carbons to hydrogen to complete their octets. Now in both cases, the molecular formula is exactly the same, C4H10, and in this case also it's C4H10. However, we can clearly see that their structures are different. The ball and stick model of both structures are also shown here. So these are the examples of constitutional isomers. Constitutional isomers can also be represented by the line angle formula. For example, in case of first structure, the line angle formula will look as that, and in case of the second structure, the line angle formula will be written as this. Hydrocarbons with 3 or fewer carbon atoms do not possess any constitutional isomer. So in other words, methane, ethane, and propane, so these are the first 3 members of alkanes. They do not have any constitutional isomer. So in other words, they can only be written by or represented by one structural formula. We must remember here that constitutional isomers are different compounds. They have different physical and different chemical properties. For example, in case of these two structure formulas, their uh, physical properties differ completely. The first structure formula, the boiling point is negative 0.5 degrees Celsius, and for the second uh, compound or the second constitutional isomer, the boiling point is negative 11.6 degrees Celsius. That's a huge difference. So how do we identify if two given compounds are constitutional isomer or not? The easiest way to identify if they are constitutional isomers or not is, first we write the molecular formula. For example, the two molecular formulas are already given here. Secondly, we find the longest chain. Now, longest chain may have a bend, uh, but it cannot have it cannot have a break between it. For example, in these two cases, for first molecule, the longest chain would be this one, and for the second one, the longest chain is this one. Remember, longest chain does not need to be linear. It may have a zigzag, or it may have bends in it, but find the longest chain. And then next step is we should number the longest chain starting from uh, the end which is nearest to the branch. In case of let's call this compound the first compound, let's call this compound the second compound. In case of first compound, either end is nearest to the chain, because so you can number from either end. So let's number it from the left hand side. So that would be number 1 carbon, number 2 carbon, number 3, 4 and 5. So in case of a first compound, the longest chain is 5 carbon long. Let's look at the second one. In case of second compound, now from right hand side, the first branch is nearest, so we have to number from the right hand side. So it would be number 1, number 2, number 3, number 4 and number 5. Both have 5 carbon long chain. So in case the longest chain are different, so the answer will be simple, so they are not constitutional isomer. But in this case, both the chain lengths are same, so there is still a chance that they may be constitutional isomer. So the next part you need to do is convert the the structure formula into line formula, because that will make it easier to identify. So first compound, I'm going to write here, so it's 5 carbon long chain. So let's draw the 5 carbon long chain. So that is 5 carbon long chain. We can number it also. This is number 1 carbon, number 2, number 3, number 4 and number 5. Similarly, for number 2 compound, we can also draw the 5 carbon long chain and similarly number it too. Now, if we look back at our structure, so we can see at number 2 carbon there is a branch, and that branch has a CH3. So let's replicate that, and we should draw a branch at number 2 carbon. So let's do that. So this would be branch. We don't have to write the CH3 because it's understood that there is a CH3 at the end. Similarly, at number 4 carbon, there is another branch. So we must replicate that also. So we should draw a branch at number 4. So number 4 carbon, we have also a branch here. Let's replicate the branches in second compound. So in second compound, uh, at number 3 carbon we have a branch, and number 2 carbon we have a branch. So let's draw those branches here. So number 2 carbon has a branch and number 3 carbon has a branch. All right, so now we have enough information. So each of these, if you count the number of carbons and number of hydrogens in both of these, the answer is same. So each of those two compounds contain 7 carbons and 16 hydrogens. But if we compare their structure, we can clearly see that their structures are different. So therefore, they have same formula, molecular formula, but different structural formula. Therefore, they are constitutional isomer. So they are indeed constitutional isomers. Carbon is one of the unique atom or element which has ability to form strong bonds with other carbon atoms, and it has ability to form long chains with other carbon atoms. Apart from carbon and up to some extent silicon, no other element has this ability to form long chains with atoms of itself. So therefore, this is one of the reason why life is carbon based, because carbon is the only molecule which carbon is the only element which can form large molecules big enough to create proteins and other macromolecules. So therefore, scientists believe that if life exists on some other planet, most likely it will also be carbon based or maybe silicon based. But anyway, the ability of carbon to form strong bonds with other carbon atoms results in a staggering number of constitutional isomers. For example, I already mentioned that methane does not have any constitutional isomer, so it has only one kind of structure. But if we go from 1 carbon to 5 carbon, um, there are 3 constitutional isomers, and if we go from 5 carbon chain to 10 carbon chain, number of constitutional isomers are 75, and as it goes further large, you can see the number of constitutional isomer goes to millions. In fact, the last one, 30 carbon long chain, so number of possible constitutional isomers is more than 4 billion. So therefore, even for a small number of carbon and hydrogen atoms, a large number of constitutional isomers are possible. Now, because constitutional isomers have different chemical properties, a rich diversity of chemistry is possible within these sets. Ideally, each hydrocarbon or each alkane should have a different or unique name. As we saw in previous slide, that even with a relatively small number of carbon atoms within the longest chain, potentially millions of constitutional isomers are possible. And in a perfect system, all those constitutional isomers should have a different name so that we can distinguish between them. For this purpose, chemists have adopted a set of rules established by IUPAC. IUPAC stands for International Union of Pure and Applied Chemistry. In next few slides, we will go over the rules established by IUPAC, and we will learn how to write names of different alkanes. The IUPAC name of an alkane with an unbranched chain of carbon atoms consists of 2 parts. The first part is a prefix, and prefix tells us the number of carbon atoms. The second part is suffix, which signifies the type of hydrocarbon we are dealing with. In case of alkane, the suffix is common for all alkane, and it is ane, which is pronounced as ane. Hence, alkanes have a suffix ane. This table gives us the prefixes which are used to identify or signify the number of carbon atoms in a chain. For example, if we have an alkane with a 3 carbon long chain, so that would be this one. So because it's a 3 carbon long chain, so we will use the prefix for 3. So prefix for 3 is prop. And because it's an alkane, then we will attach suffix for the alkane, which is ane. So hence the name of this compound will be propane. Similarly, we can build any linear alkane. By linear I mean that it does not have any branch. In case of a branched alkane, the IUPAC name has two parts. Part 1 is a parent name. Parent name is also known as root name. The parent name indicates the longest chain of carbon atoms in the compound. The second part is substituent. Substituents indicate the branched groups bonded to the parent chain. For example, if we have this compound, in this case, the longest chain will be the root or parent chain, so that would be our longest chain, and we can see the longest chain is 1, 2, 3 and 4 carbon long. And in previous slide we learned that prefix for 4 is but, and because it's all single bond, so it's alkane, so therefore suffix is ane. So our parent chain is butane in this case. However, we do have a group or a branch. So this branch or this group is called substituent. So in this example, our parent chain is butane and our substituent is this one. Now, in how do we name substituent? The name of substituent is derived by the name from the alkane part of it. So let me explain. Now substituent is only 1 carbon long. So the name for 1 carbon alkane is methane. So therefore this substituent name will be derived from methane. And when we derive the name of substituent, we drop the ane and we add YL at the end. So methane becomes methyl. And similarly, if in case we have a ethane substituent, the name of that substituent will become ethyl. Another thing to remember is the substituent is always derived by removal of one hydrogen atom from the alkane. For example, this substituent, it is CH3 because the fourth bond is bonded to the parent chain. Let's go over the rules established by IUPAC to name various alkanes. I will explain these rules with the help of various examples. So first rule is about the name of saturated hydrocarbons with unbranched chains. So this was already explained in the beginning of nomenclature. So in this case, if you have a linear alkane, so just find the prefix, and suffix in case of alkane is always ane. So for example, if we have an alkane with 3 carbon long chain, So the prefix for 3 is prop, and the suffix is ane. So the name of this alkane is propane. So these are the simplest kind of alkanes. Let's go over the rules for slightly more complex alkanes. In case we are dealing with the branched alkanes, for example, this one. So the first rule is that we must establish the parent chain. Now by rule, the parent chain is the longest chain. It may or may not be the horizontal chain, but identify the longest chain. For example, I can see in this example, the longest chain is this one. So this will be my parent chain. And then we give number to each carbon atom. So this will, let me number it. So it's 1, 2, and 3. And the substituent and both parent chain are given names. So parent chain is 3 carbon long, and we already established that the name for 3 carbon long alkane is propane. So this part is propane. We can also show the line formula. So this would be the line formula of the same alkane. In this case also the parent chain is this part, and the substituent is shown also there. Now substituent is 1 carbon long, so therefore name of this substituent is methyl, because 1 carbon is methane, and when methane is as a substituent, it's become methyl. Now, and when we write the substituent and the parent chain name together, each substituent is given a name and a number. Now name we already have given, number is given from the fact that where this substituent is connected to the parent chain. So as we can see in this case, the substituent is connected to the second carbon of the parent chain. So the substituent will get the number 2. So when we put the name together, so we first write the name of substituent, so that's 2, and we always use a hyphen between a number and a letter. So 2 methyl, so this would be the name of the substituent, and this tells us that the substituent is methyl and is connected to number 2 position, and then the parent chain propane. So the name of this hydrocarbon is 2-methyl propane. Let's take a look at another example. I'm only going to use the branched formulas. Okay, so in this case also, we first need to identify the longest chain. The longest chain is this one, and if we count the number of carbons in the longest chain, it will come out to be 1, 2, 3, 4, and 5. And now we have a substituent. Okay. Let me write the same compound one more time. Okay. Now when we number the parent chain, we can either number from the left hand side as shown here, or we can number it from the right hand side. For example, 1, 2, 3, 4, 5. Rule number 4 states that if there is only one substituent, we must number the chain from the end that gives the lower number to the substituent. Okay, so If we go with case number 1, the substituent is getting a number 4. If we go with case number 2, now our substituent is getting number 2. So according to rule, we must a number from that side which gives the lower number to substituent. Hence this is correct number and this is incorrect. So if I now if I so this is correct. So the name of this compound will be, again the substituent is methyl. The parent chain is 5, so 5 is pent and its alkane is pentane, and methyl group is at number 2 position, so it's 2-methyl pentane. Remember the hyphen. Hyphen is extremely important. If there are 2 or more identical substituents, then we number the chain from the end that gives the lower number to substituent encountered first. So for example, we have an example of this molecule. There are 2 ways of numbering. In both cases, the parent chain is 6 carbon long, so that's our parent chain. Now we can either number from left hand side or we can number from right hand side. If we number from left hand side, so our first substituent is encountered at number 3. Okay, and if we number from right hand side, then our first substituent is encountered at number 2. So we don't care about where the second substituent is. That is none of our concern at this point. We only look for when do we encounter our first substituent. So in this arrangement, first substituent appears at number 2 position, and in this arrangement, first substituent appears at number 3 position. According to the rule, the numbering which gives the first substituent the smaller number, that is correct. So therefore this is the correct numbering and this is incorrect. Okay. Secondly, if we have same substituent, for example, in this case, we have 2 substituents and both of them are methyl. Then we use prefix di, tri or tetra to represent how many substituents do we have. Remember, it is only used when we have same substituent. So in this case, we have 2 methyl groups, and first methyl group is at number 2 carbon, comma, second methyl group is at number 4 carbon. That's it, we have only 2, then hyphen, and because we have 2 methyl groups, therefore we use dimethyl. Dimethyl means 2 methyl groups. One at number 2 position, the second one at number 4, and then we complete the name by writing the parent chain, which is hexane, because it's 6 carbon long chain. So that's the IUPAC name of a bright alkane with multiple substituents. In case if there are 2 or more different substituents, we list them in alphabetical order. For example, in this case, we have substituent ethyl here and methyl here. So alphabetically, ethyl comes first and methyl comes later. And that is done when we write the name. When we number the parent chain, so we number the chain from that end, which gives the lower number to the substituent encountered first. This rule is same as the previous rule. However, if there are different substituents, such as in this case, and they are at equivalent position. For example, if we count from left hand side, we encounter first substituent at number 3 position. If we count from right hand side, then again we encounter first substituent at number 3 position. So both are equivalent. In that case, we give preference to the substituent which comes first alphabetically. So it means this is preferred because at number 3 is ethyl, and ethyl comes first in alphabetical order. So we will go with this order. So rest of the name is similar to previous rule. So all we need to do is we need to identify the parent chain. It's 7 carbon long, so parent chain is heptane. Then we identify the substituent, so we already did. So this substituent is ethyl and this one is methyl. So ethyl is connected at number 3 position and methyl is connected at number 5. So therefore the name will be 3-ethyl 5-methyl heptane. And remember, we always use hyphen between the alphabetical letter and the number. And we use commas between numbers and numbers. For example, if you're writing 3,3-dimethyl, so we use comma between numbers and we use hyphen between number and letter. And just like in any English sentence, the first letter is always uppercase and rest are all lowercase, and they're all together. There is no space between the substituent and the parent. No space here. No space between substituent and parent name. The prefixes di, tri, and tetra, and so on, are not included in the alphabetization. So, for example, the name of this hydrocarbon is, let's first find the longest chain. So longest chain is 6 carbon, so that would be hexane, and numbering is from left hand side. So at number 2 position we have 2 methyl groups, and at number 4 position we have ethyl group. So we have a 2,2-dimethyl as one substituent and 4-ethyl as another substituent. Now when we arrange them in order, we do not consider D from di in alphabetical order. That is not considered. We compare the methyl M and ethyl E to find the alphabetical order. So therefore the correct name is 4-ethyl 2,2-dimethyl hexane and not 2,2-dimethyl 4-ethyl hexane. So di is not considered to find the alphabetical order. And finally, we are on to the last rule. So it states that in case we have possibility of 2 longest chain with similar chain length. For example, in this case, our longest chain could be either this way. So this is 6 carbon long chain, or this way. This is also 6 carbon long chain. Both are same molecules, by the way. So let me clean it up. So either our longest chain is this one, 6 carbon long, or our longest chain is this one, again 6 carbon long. So according to this rule, if there are 2 or more parent chains of identical length, then we must choose the chain which contains more number of substituent. So in choice number 1, we have 1 and 2 substituents. So this is methyl and this one is ethyl. In choice number 2, we have only one substituent. The name of this substituent is isopropyl. So according to this rule, we go with that parent chain which has greater number of substituents. So this is the correct name and this is incorrect. So these are all the rules, and we will now practice few names, and that will give us an idea how to write the names of various alkanes. This table summarizes the names of alkyl group with 1 to 5 carbons, and in many cases we do use common names instead of the IUPAC name of the alkyl group. And in fact, these common names are accepted in writing the IUPAC name uh, of a alkane. And in many cases, common names are used more often than the IUPAC name. For example, uh, uh, the common name of this substituent is isopropyl, and IUPAC name of this substituent is 1-methyl ethyl. So isopropyl is used more often than 1-methyl ethyl. Similarly, this is isobutyl, common name, and this one is tertiary butyl, common name. The IUPAC name of this substituent is 1,1-dimethyl ethyl. Um, it will be a good idea to familiarize ourselves with these common names and structures of these substituents. In organic compounds, we classify carbon atoms as primary, secondary, tertiary, or quaternary depending on the number of carbon atoms it is bonded to. For example, in case of primary carbon, the carbon atom is bonded to only one other carbon. Uh, for example, in this case, the number 1 carbon, it is bonded to only one more carbon, this one. So therefore, this carbon is primary carbon. Any hydrogen bonded to primary carbon, they're all called or all known as primary hydrogens. For example, these 3 hydrogen atoms, let me clean it up. We can show it this way. So now we can clearly see that this carbon is bonded to only one more carbon. Therefore, this carbon is primary carbon. And all of these 3 hydrogens, because they are bonded to primary carbon, so these hydrogens are all known as primary hydrogens. Similarly, the secondary carbon is a carbon which is bonded to 2 other carbons. So now in this case, this carbon, we can clearly see that it's bonded to one carbon on this side, another carbon to that side. So therefore, the middle carbon here, so this carbon is a secondary carbon. And all hydrogens bonded to secondary carbon are secondary hydrogens. So therefore, these 2 hydrogens are secondary hydrogens. Tertiary carbon is a carbon bonded to 3 other carbon atoms. So we have to write another example now. We don't have to show hydrogen separately. So in this example, we can see the middle carbon. So this carbon is bonded to 3 carbons, so one on this side, one on top, and on the right side. The bottom is hydrogen, so that does not count. So therefore, this carbon is a tertiary carbon, and any hydrogen bonded to tertiary carbon is a tertiary hydrogen. So this hydrogen is a tertiary hydrogen. Finally, the quaternary carbon is a carbon, you have already guessed it, which is bonded to 4 carbons, and so this carbon is quaternary carbon. And remember, there can be no quaternary hydrogen because carbon can only have 4 bonds and it has already bonded to 4 other carbons. So therefore, it's not possible for it to bond to another hydrogen. The examples of various primary, secondary, and tertiary and quaternary carbons are shown in this slide. Cycloalkanes are those hydrocarbons in which carbon atoms are joined to form a ring. For example, in this case, we have 4 carbon atoms joined to form a ring. Cycloalkanes are generally represented by the line formula, so therefore this would be the more common representation of a cycloalkane of 4 carbon ring. The general formula of cycloalkane is CnH2n. Cycloalkanes of ring sizes from 3 to over 30 are found in nature, and in principle there is no limit to the ring size. However, 5-member rings and 6-member rings are especially common, and therefore we will study the 5-member and 6-member cycloalkane in detail in this chapter. In order to name a cycloalkane, we prefix the name of corresponding open chain alkane with cyclo. Therefore, this 4-membered cycloalkane will be named as, now we know that the 4-member open chain alkane is called butane, and because it's a cyclic form or cycloalkane, so we use the prefix cyclo in the front. So the name of this cyclic alkane is cyclobutane. Cycloalkanes can also contain substituents. For example, this 6-member ring has a substituent methyl group. If there is only one substituent on the cycloalkane ring, there is no need to give it a number. We just name it. Therefore, the name of this cycloalkane compound will be methyl. Methyl is the substituent, methyl cyclo, and it's a 6-member ring. So 1, 2, 3, 4, 5, 6. So it's a methyl cyclohexane. If there are 2 substituents, then we number the ring by beginning with the substituent of lower alphabetical order. For example, in this cyclobutane, we have a methyl substituent here and ethyl substituent here. So we will number the ring starting from the substituent which is lower in alphabetical order. So we will give this carbon number 1. And now we can either go clockwise or the anti-clockwise, but remember we number in that order where the other substituent gets the next lowest number. So therefore, if we go clockwise like this one, the other substituent is getting number 4, which is pretty large. So that's not the correct way of doing it. So the correct method will be 1 and then 2, 3 and 4. So name of this compound will be 1-ethyl 2-methyl cyclobutane. Methyl cyclobutane is a one word. I don't have enough space, therefore I'm writing them separately, but you should write it as a single word. If there are 3 or more substituents, then we number the ring so as to give the substituent the lowest set of number, and we list them in alphabetical order. As I mentioned earlier, the cycloalkanes structures are preferably shown as a line angle drawing. So this gives you an example of a cyclic compound with 5-member ring. So we represent cycloalkanes by a ring of a regular polygon that has the same number of sides as there are carbon atoms in a ring. Let's practice some of the nomenclature problems in case of cycloalkanes. Uh, so in case of A, first we need to identify the parent cycloalkane. So in this case we have a 5-membered ring. So 1, 2, 3, 4, 5. We don't have to number it because it has only one substituent, but just to know that how many carbons are there is a good idea to number it. Now the name of this substituent is isopropyl, so therefore the name of A will be isopropyl cyclopentane. In example B, now we have two substituent and the ring is 6 carbon long. Now substituent number on the right hand side, this substituent is methyl. The other substituent, this is tertiary butyl. Now although di, tri, tetra are not considered in alphabetical order, but tertiary T is considered. Tertiary is part of the name of this substituent. So methyl is alphabetically ahead of tertiary butyl. So therefore the name of, we will start the number from the methyl part. So 1, 2, 3, 4. So therefore the name of this compound will be 1-methyl 4-tertiary butyl, and it's a 6 carbon ring, so it is cyclohexane. Now in example C, we have 3 substituents. So 1, 2, and 3. 2 of them are methyl and 1 is ethyl. Now, if you have only 2, we start the numbering from the substituent which is alphabetically at lower number. However, when we have more than 2, then we start from the substituent where the overall set gets the smaller number. So therefore only possibility in this case is that we start from here. So that's 1, 2, 3, and 4. That's the only set where we get the lower number of set. So the name of this is when we write the name, then of course we arrange them alphabetically. So it will be 2-ethyl 1, 4 dimethyl cyclohexane. And finally the last one, so this was C. Last one, we have a 3-membered ring and we have a substituent ethyl and methyl on the same position. So because we have more than one substituent, now we have to number them. So we number start from here. That's 1, 2, and 3. So name will be 1-ethyl 1-methyl cyclopropane. Bicycloalkanes are those cyclic alkanes which share 2 carbon atoms in common. For example, this is a regular example of cyclic hexane or cyclohexane, and this is an example of regular cyclobutane. But when they are together and they share 2 carbon atoms, for example this way, they appear like a fused rings. In this case Now they are sharing two carbon atoms. So these kind of compounds where two cyclic compounds are fused with each other and they share two carbons together, these are known as bicycloalkanes. The shared carbon atoms are known as bridgehead carbon atoms. For example, these two carbon atoms, this one and this one, they are shared carbon atoms, so these are known as bridgehead carbon atoms. In some cases, you may have more carbon connecting the bridgehead carbons. So for example, in this case, there is additional carbon right here connecting the two bridgehead carbons. The middle carbon is known as a bridge carbon. In this case, we have only one bridge carbon, but in some other examples, we may have more than one bridge carbon compounds. For example, so in this case, we have, this is a bridge carbon, these two, and now we have two bridging carbons here. The IUPAC names of the bicyclo compounds follow the rule in which we number the bicyclo compounds starting from the bridge carbon and we number the larger ring first. For example, in this case, we start from this bridge carbon. You can start from either bridge carbon. But for example, in this case, we started from this bridge carbon and then we number the larger ring first. So that would be 1, 2, 3, 4, 5, and 6. And then we continue and number the smaller ring. So after 6, there would be 7, 8, 9. So total number of carbons in this compound is 9. And the parent name for 9 is nonane. So remember this name. And then we take a look at any carbons on the bridge. If there is any carbon on the bridge, in this case there is no carbon, we will also number it. So to arrange the name, so we start with the word bicyclo and then square bracket. That's important. In the square bracket, we write the number of carbons in first the larger ring except the bridge. So we do not include the bridge. So other than the bridge, how many carbons are present in the larger ring first? So in this case, we have 1, 2, 3, and 4 carbons. So therefore, we write the number 4, comma. Now, number of carbons in the smaller ring except the bridge. So that would be 1, 2, and 3. So therefore, we write 3. And then we look for any carbon on the bridge. Not the bridging carbon, but any extra carbon on the bridge. In this case, there is no extra carbon in the middle, so therefore we write 0 and then square brackets close and then nonane. So in the second example again, we can see that apart from the bridge, there are 4 carbons in one ring and 4 carbons in the other ring. In other words, it's a symmetrical ring, so you can count from the either side. The name will not change, so the name will be bicyclo 4 dot 4 dot, so it's dot, sorry, not commas, and 0 decane. Now this is interesting because in this case there is 1 carbon on the bridge. So when we number them, so again both left and right side rings are the same size, so it doesn't matter which side you count. So we start from here, so 1, 2, 3, 4, 5, and 6. So apart from the bridge, in the larger ring we have 2 carbons, therefore this is 2. In the smaller ring again there are 2 carbons, therefore this is 2. and there is one extra carbon on the bridge, that's why it's 1, and total number of carbon is 7, so it's heptane. For bicycloalkanes, common names are more prevalent than the IUPAC name. For example, in these cases, the first compound is hydrindane, the second one is decalane, and the third one is norborane. So these are more commonly used than the IUPAC names.